Hello everyone. The title of this video is First Order Linear Systems in Matrix Form. Alright, so we're going to be taking a look at a system of linear differential equations, first order linear differential equations, and going back and forth between writing it in normal, what they call normal form, and writing it in what they call matrix form, expressing the system as a matrix equation. So let's take a look. Okay, so my first examples are going one way to the other. So the way I have the system of equations written right now is called normal form. I'll write that here, where all the first derivatives are on one side all by themselves alone, and then everything else, x of t, y of t, and then some other functions of t, where t is the independent variable here, on the other side. Okay, now I'm asked to write the given linear system in matrix form. Now matrix form looks like the following. Right. So I have on the left side a vector, so I'll do like a capital X with a little arrow for a vector x prime, meaning the derivatives of vector x, the components of vector x, which I'll get into what vector x means in a second, equals some matrix A, and this is going to be an n by n matrix, a square matrix. So in this case it'll be, since there are two equations and two unknown functions, x and y, it's going to be a 2 by 2 matrix, multiplied by another vector x. This is the function vector, with x of t and y of t, and then plus some other vector called f, which is going to be consists of functions of t, right, functions of the independent variable. So again, I'll write out what these mean, where the vector x in this two equation, two unknown function system, the vector x just consists of those unknown functions. So x of t for the first component, y of t for the second component. And when we get into three equations with three functions, the vector x will be a 3 by 1 vector. X prime, this vector x prime, is simply made up of the derivatives with respect to t of each of the components of x. So x prime of t, y prime of t. And again, this vector f is just made up of functions of t. So say f1 of t and f2 of t. And if this vector, this f vector, if that's the 0 vector, so if f is the 0 vector, then the system is going to be homogeneous, and the system is considered homogeneous. And if this f vector is not the 0 vector, then the system is non-homogeneous. And in this video and in future videos on solving systems of equations, linear equations, our matrix, our n by n matrix A, is made up of the coefficients of the functions x of t and y of t. And for the most part, we're going to be considering just systems where those coefficients are constants. All right, so not other functions of t itself. Okay, so this here, this matrix written in normal form, again, I think it's pretty easy to translate from normal form to matrix form and vice versa. This left side, we have dx dt dy dt, that's x prime y prime, that's the vector x prime. Right, vector x prime equals. And then if we think of, again, if we think of each of these as vectors, right, this is a 2 by 1 vector over here, and this is a 2 by 1 vector over here, right, two rows, one column. We could split this 2 by 1 vector up into the product of, a matrix A and the vector x, where the vector x again consists of the functions x of t and y of t. Right, I could think of this as the following. Right, the matrix 3, negative 5, 4, 8. Right, this is a 2 by 2 matrix, where down the first column I have the coefficients of x, down the second column I have the coefficients of y, and then multiplied by the 2 by 1 matrix, 2 by 1 column vector, x, y, or x of t, y of t, same thing. When you see x and y, you have to know that they're functions of t, right? The derivatives are with respect to t here. And this is how we're writing this in matrix form. So I'd write this as, this is my matrix A, this one with the coefficients 3, negative 5 for the first row, 4, 8 for the second row, and then times, vector x. Again, this is the vector consisting of the unknown functions in the system, x of t and y of t, in that order. And that's it. Right, and there's nothing else accounted for here. Right, there's no other functions of t being added on at the ends of these equations. So this would be considered a homogeneous system. Right, because that f vector that I mentioned earlier is the 0 vector, right? I'd have plus 0, plus 0. So I just want to point that out, right? This is an example of a homogeneous system. But it's as simple as that. Alright, so I've got another couple examples of this that are pretty quick and easy. Again, especially if you've taken some sort of linear algebra course before, this should be pretty straightforward. Right. So here's another example. I'm going to write the given linear system in matrix form. This time, though, got 3 unknown functions, x of t, y of t, and z of t. So this time, the vector x in question that I mentioned earlier is consisting of the components x of t, y of t, and z of t, or just x, y, and z. It's a 3 by 1 column vector. And then x prime, right, vector x prime would be consisting of x prime, y prime, z prime, or dx dt, dy dt, dz dt. So I can very quickly and easily write this in matrix form. The left side is just the vector x prime, right? It has these 3 components, x prime, y prime, z prime. Equals, and then a matrix A, where this time, three equations, 3 unknown variables, 3 unknown functions. So it should be a 3 by 3, right? A 3 by 3 coefficient matrix. And then just as before, the coefficients of x down, I'll put them in the same order that I put them in the vector x, then y, then z. So the coefficients of x down the first column, so negative 3, 6, 10, right? Then the coefficients of y down the second column, positive 4, negative 1, and then positive 4. And then the coefficients of z, right, down the third column, so negative 9, 0z, right? You can technically think of this as plus 0z, so 0, and then positive 3. and then times vector x, right? This matrix 3 by 3 times this vector, the 3 by 1, would give me the resulting setup on this side. Again, if you thought of this as a 3 by 1, this whole side here is a 3 by 1 column vector, multiplying this matrix by that vector would give me negative 3x plus 4y minus 9z in the first row, 6x minus y in the second row, 10x plus 4y plus 3z in the third row. And that's it, right? There are no extra functions of t to make up that vector f that I mentioned, right? So here's the a times x, plus f, where, this f is yet again the 0 vector, right? And since this f is the 0 vector, we have another example of a homogeneous system. Oops, sorry. Should have brought that up more. Homogeneous system. Okay. Again, pretty easy, I think. Pretty straightforward. Pretty quick to do. I got one more. Now this time, the first two examples were of homogeneous linear systems of first order. This time, I have these functions of t that are added on after the x, y, z terms, right? First one I got x minus y plus z, then plus some function of t, right? T minus 1. Then second equation, 2x plus y minus z, and then plus some function of t, negative 3t squared. And then third equation, x plus y plus z, and then again, plus some function of t. Alright, so this, again, the vector x, the vector x is yet again made up of the three component functions x of t, y of t, and z of t, or just x, y, and z. But this time, that vector f that was mentioned right back in the matrix form on the first page, right, this vector f is not the 0 vector this time. So the vector f is, for the first component, the first row there, first equation, t minus 1. And then negative 3t squared. And then t squared minus t plus 2. There's this vector f. And then writing this as a matrix equation, we have, the dx, x prime, y prime, z prime, that's vector x prime. Then we have all the stuff with x, y, and z involved, right here, which I can write as a matrix times vector x. Now, again, the matrix I'll put in the same order, x, y, z. The coefficients of x down the first column, 1, 2, 1. Coefficients of y, negative 1, 1, 1. Coefficients of z down the third column, 1, negative 1, 1. Alright, and this would be times vector x, and then plus vector f. Alright, plus that vector f. Now you could also just write it out again, but there we go. And again, notice that this vector f is not equivalent to the 0 vector, right? It has values other than 0 for different values of t. So here is an example of a non-homogeneous system of equations. Alright, and again, solely because of this vector f not being the 0 vector. Okay. So again, hopefully pretty quick and easy being able to write a system in normal form in this matrix form. Alright, so now I'm going to go the other way around. I'll be given a matrix form system, a matrix equation, and write the system in normal form, right, the way that all these examples started. So I've just got two of these. Right. So here it is the other way around. Right? Write the given linear system without the use of matrices. Right. So again, just recall here. Now this is this coefficient matrix being a 2 by 2 system, 2 by 2 matrix. Vector x would have to be a 2 by 1. So we have two functions of t, x of t, that I'll call x of t and y of t. I mean, you could also call them x1 and x2 if you wanted, but all right. So let me fill all this stuff in. All right, x prime, right, this vector would be just x prime of t, y prime of t equals. Now, I'm still in the matrix form. All right, we'll get out of it in a second. I just wanted to refresh your memory as to how to do matrix multiplication. Just replacing vector x with the x and y of t plus, and then again, hopefully you recall how to do multiplication by a scalar. I know e to the t isn't a constant, but this is the same as multiplying each component by e to the t. So I have 1 e to the t for the first component of this vector f, and then negative e to the t for the second component. Now comes matrix multiplication. Now remember, a 2 by 2 multiplied by a 2 by 1 will be a 2 by 1. And remember how this works. You do a lot of these, dot products. For the first row, first column of the product, I do the first row of the left matrix dot product with the first column. So this would be 4 times x plus 2 times y. I'll just write 4x plus 2y. Okay, just understand that when you see x and y, they are functions of t. And then for the second row, first column, I take the second row of the left matrix dot product with the first column. That'd be negative x plus 3y. All right, and then I have again this plus, e to the t, negative e to the t. And now I can write this in normal form, where the left side equations, all the first row elements belong in an equation. So I have, x prime or dx dt equals 4x plus 2y, and then plus e to the t. All right, the first row, first column component of the right side must be equal to the first row, first column component of the left side. And that's what this equation states. And then the second row, first column components must be equal as well. So I have dy dt, or y prime, equals, and then negative x plus 3y plus e to the, minus e to the t. So just there. And there we go. Right, here's this system that started off in a matrix equation written in normal form. Okay. So without a matrix, as two equations separately, with these two unknown functions x and y. And of course, again, this is an example of a non-homogeneous, because of this e to the t minus e to the t, right? That this is the vector f that was mentioned earlier, which is clearly not the zero vector. Right, so another example of a non-homogeneous system. Right. Great. All right, I've got one final example where I'm just going to kind of write it out pretty quickly. All right, hopefully you can see it. This time, my matrix of coefficients here is a 3 by 3. So vector x is going to consist of three functions, x, y, and z. Or you could say x1, x2, and x3, right? But I have three unknown functions in this system. So then x prime would have x prime, y prime, z prime. So I'll just tell you right now. Let's just make this real easy. First equation. would have, dx dt equals. And then the first row of this corresponds to 7x plus 5y minus 9z. And then look at the first row here, plus 0 times e to the 5t, so plus nothing. First row here, minus 8 times e to the negative 2t. So this is all the first row stuff, making one equation. Then all the second row junk. We have dy dt, all right, y prime, equals, and looking at the second row here, the 4, 1, 1, that would correspond to 4x plus 1y plus 1z. Second row here is, plus 2 e to the 5t. And then second row here is minus nothing, right, minus 0. So there's all the second row stuff equated. And then third row, z prime or dz dt equals, and then the third row of this matrix, 0, negative 2, 3 would correspond to 0x minus 2y plus 3z plus, third row here would be 1 e to the 5t. And third row here, minus 3 e to the negative 2t. And there you go. Here's the same system. These mean exactly the same thing. All right, same system, mean exactly the same thing, only this one's written as 3 separate equations without matrices. And of course, once again, now this entire thing here, right, all of this would be considered vector f if you want to put them together as a single vector. And that's clearly not the 0 vector, so this is another non-homogeneous. I'll just put NH, right? Non-homogeneous system. Alright, so hopefully going back and forth from normal form to matrix form seems simple enough. I did a few pretty quick examples here. And your ability to go back and forth, that'd be a nice thing to be able to do pretty quickly, especially when we get into solving these things, finding solutions of these systems. And yeah, hopefully this helps you out. Watching me go over these several examples helps you out when you're working on problems similar to this. Thank you very much for watching.